welcome you all to this video. Today we discuss steady state error for unity feedback system. In previous video we just look at what is steady state error, and we come to know that the steady state error is defined as the difference between the tracking input and the output that is achieved by the system. If there is a difference, we call it as a steady state error, and it is calculated for stable system and calculated when transient responses over. After steady state time, you will calculate the difference between input and output, and this difference is known as steady state error. So now this section is 7.2, where we discuss steady state error for unity feedback system. So the whole terminology we develop here is for unity feedback system. So we assume that we have steady state error that is calculated for closed loop transfer function, and we represent the closed loop transfer function by T of S, okay, or open loop by G of S. Okay, so you have to remember that. What do you mean by open loop and closed loop? Closed loop means that because we have a unity feedback system, so we have only G of S available in a loop, and H of S is 1. So when we calculate the closed loop transfer function, that is T of S is equal to G of S divided by 1 plus G of S. Okay. Now, so how we will calculate and define this thing? Let's consider we have a steady state error in terms of a closed loop transfer function, that is T of S. Okay, now error is actually between the input and output. So our input we represent in terms of R of S, and output is C of S. Okay, and we know that what is transfer function? Transfer function is actually ratio of output to input, that is equal to T of S, or we can write the output as C of S equal to R of S times T of S. If we plug back this relation to equation 7.2, it becomes E of S equal to R times 1 minus T of S. So here if you look at, we represent error in terms of closed loop transfer function. Now because we are looking for steady state error, or in other words, we are looking for error when we have transient responses over. So we do, if you remember, we do study final value theorem, FVT, final value theorem, when we study the Laplace. So final value theorem help us to identify the steady state value of the output. So here we can apply the final value theorem to calculate the error value. So for that reason, we can solve for E of t at any time. We are interested in the final value of the error, that we represent it as E of infinity. So final value we normally represented for error is as E of infinity. Applying the final value theorem, which allow us to use the final value of et without taking the inverse Laplace. So means that we can find E infinity equal to limit when t tends to infinity E of t. Instead of calculating time response, we directly apply theorem on this equation 7.4 as limit when s tend to 0 s time E of s. So when we plug in the values of E of s in this relation, so E infinity becomes limit when s tend to 0 s time R of s times 1 minus T of s. So this way we can easily calculate the steady state error. So we can apply the final value theorem. So you remember when we study the final value theorem, there's some condition for final value theorem is that it is applied only when we have stable system, means that poles of the closed loop system must be in left of plane. So this condition is also applied here. This only calculates for stable error. If error is growing, this formula is no longer work. Okay, so that's why the steady state error will, for calculating steady state error, our system must be stable, or in other words, poles must be at the left of plane. Now there's a question, an example, and it says that find the steady state error for the system in figure 7.3a if TFS and the input is a unit step. Now, we know the closed loop transfer function here. We can easily calculate the error. So for unit step, we can write the R of S as 1 over S because this is the Laplace of unit step, and this is a closed loop system. Now, if we calculate error, so we will use this equation, that is 7.4, to calculate EFS, that is R of S times 1 minus TFS. So plug in the TFS value here, 1 over RS here. You can calculate error easily, and error becomes S square plus 7S5. This is the error equation. Now question is, find the steady state error. So if we look at the poles here as closed loop transfer function poles on the stable on the left of plane, so there's no right of plane poles for this one when we can look at the pole, so we can apply the final value theorem. So final value theorem usually applied taking the limit s into EFS, so s will cancel out. When I put 0, it becomes 5 by 10, that is 1 by 2. So steady state error easily calculated using the final value theorem without taking the inverse Laplace. Now this is the calculation when we have closed loop transfer function. In most of the cases we don't have the closed loop transfer function, but instead we have open loop transfer function. Now if we have open loop transfer function, that we call it G of S. So how we can calculate the error? So we will do the same thing. So we know that error is equal to R minus C of S. Now C of S can be calculated as, if we look at the transfer function with respect to error, error as an input and output, so we have G of S. Okay, now we can calculate the error relation, that becomes 1 over 1 plus G of S. So you just rearrange the block diagram and you can easily calculate the transfer function with respect to input and error, that becomes 1 divided by 1 plus G of S. Just multiply by R of S, you calculate the EFS. So this means that EFS and open loop transfer function has a relation, that is R of S divided by 1 plus G of S. Okay. Now to calculate the steady state error, we have to take the have to apply the final value theorem, and we can easily calculate E infinity, that is limit when S tend to 0, S into R of S divided by 1 plus G of S. This is a very important relationship that we use a lot. This is 7.11. So this allows us to directly calculate the steady state error using the open loop transfer function and input of the system. Now because we have different possibilities for the input, so assume that we will look at some few inputs and see how steady state response behaves. So first input is the step input, if you remember. So in the table sample 1 we discuss different inputs. Now here we are looking for the first input, that is step input, and we say that it is represented by 1 over S. So we just plug in 7.11 R of S by 1 over S and just solve the steady state error, and we just write here step so that we know that we are calculating error for step input. When we do that, S will cancel out and we left with 1 over 1 plus limit when limit G of S. Okay, the term that is limit S tend to 0 times G of S is the DC gain of the forward transfer function. Okay, so since as the frequency variable is approaching 0, in order to have 0 steady state error, so for that case this must be equal to infinity. So now Otherwise, you do have some constant error. Because you make this infinity, then this big 1 over infinity becomes 0. So hence, to satisfy equation 7.13 must take on the following form. So this is only possible if you have s here, because when you can have some s that is separated and you put s equal to 0, then you can easily calculate then this term becomes 0. So in other words, for step input with a constant error can be 0 if we have an integral in the system. Okay. So to look at this, we say that if we write a open loop transfer function in terms of zeros and poles. So look here, we have z1 is the first zero, z2 and so on. Similarly, we have poles p1, p2, but we also have n poles at the origin. So s power n means that s equal to 0, or in other words, we have poles at the origin. And for the limit to be infinite, the denominator must be equal to 0 as s goes to 0. So this is the basic idea. Thus, for n is greater than or equal to 1, that is, at least one pole must be at the origin, hence divided by s in the frequency domain is integral in the time domain. We are also saying that at least one pure integral must present in the forward path. The steady state response for this case of zero steady state error is similar to the shown in figure 7.2 output 1. If you remember, we discussed output 1. So the main idea is that to make steady state error 0 for step input, you need a single integral. Okay. So if there is no integral, so this means that if I consider this as a open loop transfer function, which is a generalized one, plug in the limit when s tends to 0, you come up with some constant values, which is finite and yields a finite error according to this equation 7.12, because this has some finite number. So 1 divided by 1 plus some finite number, you get some constant steady state error. Okay. In summary, for step input to a unit feedback system, the steady state error will be 0 if there is at least one pure integral in the forward path. So the main idea that we learn from here is that if you have open loop transfer function and you have at least one integral available, then steady state error to the step input is 0. If there is no integral available, then you have a finite steady state error. So this means that when we discuss the number of poles at the origin, so if you have at least one pole at the origin, so in that case you have a pure integral and that makes the steady state error 0. Otherwise you do have a constant steady state error with step input. Okay. Now comes to the next input, that is known as ramp input. Now when we look at the ramp input has two poles at the origin. Step input has one pole at the origin. Now ramp input has two poles at the origin. When we consider the same type of transfer function, that is the equation 7.12, and calculate the E infinity, that is E ramp of infinity, that becomes limit when s tends to 0, s into 1 over s square, 1 plus g of s. When we plug in the value, so it becomes 1 over limit s into g of s. So this is the basic idea. If g of s has no integral, then this error is 0. If g of s some integral, then we have a finite error. So we will look this. So 7.14 is when we have a ramp input. So you look at, there's a difference between when we look at the ramp input and the unit step. For unit step, we have equation 7.12, which is 1 over 1 plus limit s tends to 0 g of s. but in case of ramp we have 1 over limit s into g of s. Now we want this equal to infinity so that we have zero steady state error. So for that case, it is only possible uh, if one integral exists in the forward path, then we have a constant error. Okay. So if there is no integral in the g of s, then we can say that this is possible because you have a constant value and you multiply by with s and you take the limit, it becomes 0. So if there is no integral, then we have 0. Otherwise, we have, and the steady state will be infinite. And if there is no integral in the forward path, then uh, because this becomes 0, when this becomes 0, and if we look at the if this term becomes 0, if g of s is a finite, means that it has value that is 7.15, that gives you a finite number. When you take the limit, it becomes 0. 1 over 0 is infinite. So you need at least one integral, otherwise you have what you say infinite error. Okay, our system diverges. So it is stated that steady state error would be infinite and lead to divergent ramp as shown in figure. Output 3. Finally, we repeat the development of a parabolic input. Now, what we learned till now is that when we have a step input, we need at least one integral so that output is so that steady state error is 0. But when we have a ramp input, we need a single uh, integrator so that we have finite error. Otherwise, error is infinite. For 0 uh, error for ramp input, we need at least two integrals. Now we look at, we're moving to the third input, that is the parabolic, and we know that from the table 7.1, parabolic input is 1 over s cube. Now when we put in 1 over s cube, so it becomes 1 over limit s square g of s. Okay. So for steady state error 0, we need this limit is equal to infinity. Okay. So this is only possible with infinity when g of s has 3 integrals. Otherwise, this is not the case. Okay. So look here, when n is greater than or equal to 3, then this is possible that if we have 3 integrals, then for parabolic input we have 0 steady state error. Otherwise, if g of s has no integral or there are only 2 integral in the forward path, then we have some finite number. If there are 2 integral, then we get some finite number because second integral cancel out this s square and we left with g of s, and g of s has some constant value, so in that case we have some constant steady state error. Other than that, if you have less than 2 integral, then this term becomes 0 and you have divergent behavior, means that steady state error is infinite. Okay. Now let's do example. Example says that find the steady state error for input of 5 u of t. So what do you mean by 5 u of t? We have a step input with amplitude of 5, then 5t u of t. What this means? This means that we have a ramp input with 5 amplitude. Similarly, 5t square u of t means that we have a parabolic input with 5 amplitude. Now we have this unit feedback system where g of s is given to us, and this is, so to calculate the step input, we just write the formula for unit step. You remember from 7.11 that E infinity is equal to E step of infinity, which is becomes R of s divided by 1 plus limit s tend to 0 g of s. So R of s is actually um, when we take the limit and with the multiply by s will cancel out. We know that r of s is 5 by s, so s will cancel out with the s. When we apply the final value theorem, it becomes 5 divided by 1 plus limit s tend to 0 g of s. So when we look at this is our g of s, and we look at the limit when s tend to 0, this term becomes 0, this term becomes 0, this term becomes 0. We left with 120 into 2 divided by 3 into 4. So when we solve it, it becomes 20. Okay. Now when we calculate for step input, the steady state error becomes 5 by 21. Now next we have to calculate for ramp. When we do that for ramp, it becomes 5 divided by limit s into g of s. This is the standard form that we develop in 7.12. Okay, so we just plug in the values 5 divided by s into. So when we plug in the values, because this is a finite number, s is 0, it becomes 5 by 0, that is infinity. So for ramp input, for this unit feedback system, the error is infinite. Now let's look at the parabola. If ramp is infinite, you normally know that parabola is also infinite. So just look at here. So we just write the formula for parabola, that is because 10 divided by limit s square g of s. When we plug in the value, it becomes 10 by 0 is equal to infinity. How we get these equations? We will use this formula. Okay. For example, this is for parabola, right? If we look at, this is for ramp input 7.16. 7.12 is the step input. Okay, remember this. So we use these formulas to solve this example. Now let's do another example. So this is example number. Now this is laboratory skill problem. You have to do it yourself. I just guide you how you can do it. So we have a unity feedback system and GFS is given. Find the steady state error for the following input. We have 15u, we have 15tu, and we have 15t square u of t. Okay. So how you calculate this? So you just use the formula. GFS is given to you. Just plug in the values as we did in previous example. You get the solution. So the closed loop system is stable. Then for 5u of t, step input is 0. If step is 0, ramp must be finite number and parabola must be infinite. So this is the basic way. As you go for higher inputs, your error keep on increasing. Okay. Now the closed loop system for second one is unstable, so calculation cannot be made here. Why it is unstable? Look here. Due to two poles at the origin. So when we plot the poles for closed loop system, so this becomes unstable. So here what we study today is look at the steady state error for different inputs. We will continue further in next video about static error, constant, and system type. That is the most important topic that we developed from these two videos, and this is actually the crunch of how we define static error, constants, and system types, so that from there we know that what type of error we are expecting from the system. So thank you.